Let's see a set of examples for the transformation method. And this set of examples is what I call the family tree of well-known distributions. And you'll see why I call it that in a moment. From previous stats classes, you have learned many well-known and useful discrete and continuous distributions. For example, the standard uniform distribution, we can denote that by u of 0 from 0 to 1. We have already seen how that can be useful last time. The standard normal distribution, which we usually denote by z, which follows the normal distribution with mean 0 and standard deviation of 1. The chi-square distribution with new degrees of freedom can be really useful for doing chi-square independence tests. And that can be denoted by chi-square with nu in the parentheses. The student t distribution can be really helpful for doing t-tests. A t distribution with new degrees of freedom can be denoted by t of nu. The F distribution can be useful for doing ANOVA tests. An F distribution with m and n degrees of freedom can be denoted by f of m and n. The exponential distribution, which we've seen last time in an example, with rate lambda, can be denoted by exponential of lambda. The gamma distribution is a more general distribution compared to the exponential. It has parameters called shape of A and rate of lambda, and that can be denoted by gamma of A and lambda. And lastly, the beta distribution, which we also saw last time, and we mentioned that it's helpful for modeling proportions between 0 and 1, takes parameters A and B, and that can be denoted by beta of A and B. I haven't included a lot of the famous distributions here, such as the Bernoulli, binomial, Poisson, etc. But here are just some examples of distributions that you might have known, and it shows you that each of these distributions are actually quite different. Their uses are quite different, and they look quite different. However, it turns out that many of them are kind of relatives to one another. In other words, transforming one or more of them will result in another. Here's a plot that summarizes the relationships between these kind of different well-known distributions. In each of the bubbles is a distribution family, such as the standard normal, the t distribution, the chi-squared, the Poisson, the gamma, etc. And each of the solid arrows here indicates that we can apply some transformation function and convert one distribution to be distributed according to another well-known distribution. So this really looks like a family tree to me, and it kind of reminds me of the extended family trees of royal houses in ancient Europe, say maybe 200 or 300 years ago. In that case, in ancient Europe, you'll probably find that the king of France is actually an in-law to the king or emperor of the Ottoman Empire, etc. So these distributions, which look really far away and really not similar, are actually related to each other in some ways. So that figure is kind of overwhelming, like any kind of extended super large family tree. The complete figure, if you're interested, with maybe 25 or 35 distributions, can be found in this paper I have listed here. I included a hyperlink so you can read it and get familiar with these distributions if you want. However, here, let's take a look at a subset of the relationships between these well-known distributions and see how we can obtain draws from a distribution by transforming draws from another distribution or from other distributions. The examples week2.rmd file is the R Markdown document that contains the R code for implementing this week's examples. Let's see a total of 4 concrete examples. In these cases, we sample from an original distribution, let's say y, and then by applying some transformation, it results in another well-known distribution that we are familiar with. And let's start with a simple example where we want to transform the standard normal random variable to a random variable that is normally distributed with mean mu and standard deviation of sigma. Let's suppose that the random variable z follows the standard normal distribution. So normal distribution with mean 0 and standard deviation of 1. And let's consider the following linear transformation, h of z. Here, h of z is equal to sigma, a scalar, times z, plus mu, a constant. In this case, it's quite easy for you to see that h of z will follow the normal distribution with mean mu and standard deviation of sigma. The code below applies the transformation method to draw 1000 samples from x that follows normal distribution with mean 50 and standard deviation of 10. But we're not directly drawing from this distribution. Instead, we first draw from z, and then we apply a transformation so that it becomes this target distribution. Here, we first sample the standard uniform random variables. Let's call it the vector of z, which contains 1000 draws from the standard normal distribution. Again, we use the rnorm function in R to implement this. We're not supplying the mean and standard deviation parameters inside this function. So by default, it assumes that the mean is 0 and the standard deviation is 1. Now, let's apply the linear transformation h. We'll say that mu is a scalar which is equal to 50 and sigma is equal to 10. And then we transform z as follows. We create a new vector x, which is going to be equal to sigma times z. Z is the standard normal variables we just drew, plus mu. And let's see if our x is actually distributed like a normal random variable with mean mu and variance of sigma squared. Again, we look at the empirical and the theoretical density of our x's that we have drawn. We first create an empirical histogram of the density, the relative density. So that can be done just like last time using the hist function. We plug in the x's, which are the draws that we have obtained, and we say frequency equals f, telling it that we want to plot the density instead of the frequencies. On top of this, we overlay the theoretical density or PDF of the normal 50-10 random variable. Again, we first create a equally spaced sequence of possible x values, and then we include the red curve on this empirical density plot, where the x-axis is the possible values of x, the y-axis are what is returned from the d-norm function for each of these possible x's when the mean is 50 and the standard deviation is 10. And then we specify that type is L, meaning that we want to draw a curve, and the color is red. You can see that in this case, the empirical density and the theoretical PDF actually agree for the x. This means that by applying the transformation on the standard normal z's, the x's that we have obtained does indeed seem to follow a normal distribution with mean 50 and standard deviation of 10. Now, let's see a slightly more complicated example. So there's a well-known result that if we have a standard normal random variable z, and we apply the transformation z squared, so hz is equal to z squared, then the resulting hz follows the chi-square distribution with 1 degrees of freedom. Now let's suppose that we want to obtain 1,000 draws from the chi-square distribution with 1 degree of freedom. Let's call this random variable x. What we can do is to first draw 1,000 samples of z, and then we take the square of that. And the resulting outputs should be chi-square distributed with degrees of freedom of 1. So here's the code that implements this, and there's just 2 lines of code, so it's quite simple. First, we draw the z's, and z's are standard normal random variables. We draw 1,000 of them, and then we say x is equal to z squared. So we apply the square transformation. And again, let's take a look at the empirical versus the theoretical density of the x's that we have obtained. Ideally, the draws x's that we have obtained should have very close distribution to the theoretical density of the chi-square distribution with 1 degree of freedom. Again, let's first graph the histogram of x, which are the samples that we have obtained. Frequency equals to f in the case that we want to draw the density. And then here you can see that I plug in some additional arguments. This is because if we do not restrict the range of the x-axis, the chi-square random variables, where our x here can actually stretch out to quite far. So let's say that we only want to plot it for values between 0 and 5, which actually probably accounts for the vast majority of the possible values. Then in this case, what I can do is as follows. I specify that the x-lim is from 0 to 5, meaning that the x-axis will range between 0 and 5. But also, I need to specify the breaks for the histogram. That is how the bars will be separated. In this case, we say that breaks is the sequence from 0 to 5 with interval sizes of 0.5, as well as a last bar from 5 to the maximum value of x, which is not plotted here. However, this will allow us to plot the histogram in this range between 0 and 5. So on top of this empirical density, let's overlay the theoretical density for the chi-square distribution with 1 degree of freedom. This can be applied using the d chi-square dCHISQ built-in function in R by specifying that the degrees of freedom parameter is equal to 1. So here, we again overlay a red curve where the x-axis is the possible values of x between 0 and 5 with increment of 0.01, and the y-axis is the PDF at each of these possible x's with 1 degree of freedom for the chi-square random variable. And we can see that again, they seem to agree. So that's great news, meaning that we can apply the square transformation of the z, and the resulting samples has a distribution that agrees with the theoretical density of chi-square 1. Okay, so the 2 examples we have seen so far is the case where the original variable, or the variable we sampled from, the y's in the slides, actually is a univariate random variable. Let's now see an example, the third example, where the transformation is from a random vector. This is the transformation from chi-square to the F distribution. Let's suppose that our y, which is the ones we want to sample from, is a random vector with 2 random variables. y1 follows the chi-square distribution with m degrees of freedom, and y2 follows the chi-square distribution with n degrees of freedom. In this case, bold y is the vector of y1 and y2. Let's further suppose that our h function, the transformation function, is defined as follows. It's equal to y1 divided by m, the degrees of freedom of y1, over y2 divided by its degrees of freedom, n. So if our h function is defined this way, then x, the output of applying h to y, will follow an f distribution with m and n degrees of freedom. So let's try to use this theoretical result and draw 1,000 samples from the f distribution with degrees of freedom of 2 and 3, respectively. It should be chi-square samples here. I probably forgot a slash in the LaTeX slides. So let's try to apply the transformation method where we first draw from chi-square, and then we apply the transformation and convert that to f-distributed samples. So again, the code is quite simple. We only have 3 lines. We first draw y1, which will follow the chi-square distribution with degrees of freedom 2, as we have seen over here. y2, let's draw 1,000 samples from the chi-square distribution with 3 degrees of freedom. So n equals 3. And now let's apply the transformation. Here let's set a new vector x to be the ratio between y1 divided by 2 and y2 divided by 3. And hopefully we can see that the x's that we have obtained this way has the same distribution or very similar distribution as the f distribution with 2 and 3 degrees of freedom. So let's see if that's the case. Again, we plot the empirical density of the x's that we have drawn, and then we overlay the theoretical density. So in this case, the theoretical density for the f distribution is obtained using the df built-in function in R, and that gives you the PDF or the density of the f distribution. You need to specify the 2 degrees of freedom parameters for the f distribution here. So the first one is 2 and the second one is 3, as we have indicated here. And we can see that again, the empirical distribution and the theoretical distribution agree, meaning that the x samples that we have obtained from the chi-square samples, our y1, y2s, actually indeed follows the f distribution with 2 and 3 degrees of freedom. Okay, let's see one last example for this part. And this is an example that does not involve the z or the chi-square distributions. So it's a relatively new one. And that's from the gamma distribution to the beta distribution. Let's suppose that y1 follows the gamma distribution with parameters a and lambda, where a is the shape and lambda is the rate. y2 follows gamma distribution with parameters b and lambda, where b is the shape of y2 and lambda is the rate of y2. And in this case, y, bold y is again y1 and y2. I forgot a transpose here, but you get the idea. And our h function is defined as follows. It's going to be equal to the ratio between y1 and y1 plus y2. You can actually show, we're not going to show it here. If you're interested, you can show it or read a proof of it online. That if we apply the h function to y1 and y2, which follow the corresponding gamma distributions, then the resulting x, which is equal to h of y1 and y2, will follow the beta distribution with parameters a and b. A and b. So last week, we used the acceptance rejection method to draw samples from the beta distribution with a and b both equal to 2. This week, let's try to draw 1,000 samples from beta to 2 again, but instead of using the rejection method where we will throw away some samples, let's try to use the transformation method and rely on the results over here. So here let's create, so here's the code that implements this. We first sample the y1 and y2s from the gamma distributions. This can be done using the R gamma function in R. So y1 is going to be equal to R gamma. So 1000 samples we draw from the gamma distribution with shape A equals 2 and rate lambda equals 1. The rate here is arbitrarily chosen. We just chose lambda equal to 1 here for convenience, but you can set it to something else. As long as the lambdas for y1 and y2 are the same, it should work. Similarly, we draw y2, again R gamma. We draw them from the gamma distribution with shape of 2 and 1. So although both of them are having shape 2 here, note that for y1, the shape corresponds to the A parameter. And then for y2, this shape corresponds to the B parameter. Now, let's apply the H transformation. So let's create a new vector x that is going to be equal to y1 divided by the sum of y1 and y2. And theoretically, x should follow the beta distribution with a and b both equal to 2. And indeed, it does. Again, when we plot the empirical and the theoretical distributions, so the empirical of the x's that we obtained from the transformations and the theoretical distribution of beta to 2, we can see that the two of them agree. Okay, so we've shown 4 of these possible transformations of well-known distributions. We sample from one distribution, apply some kind of transformation, and then we can obtain x's that follow another well-known distribution. So other than the ones that we have shown in the R code, here are several additional notable relationships between well-known distributional families. The first one concerns the t distribution. Let's suppose that z follows the normal distribution with mean 0 and standard deviation of 1. And suppose that there's another independent chi-square random variable. We call it v, and that follows the chi-square distribution with new degrees of freedom. In this case, if we say t equals the ratio between z and the square root of v divided by its degrees of freedom, then this t is t distributed, student t distributed, with new degrees of freedom. So this is one way that we can use the z and the chi-square distributions and transfer that to the samples from the t distribution. We're not going to show it here. However, when you do your homework question 4, it requires you to use this relationship and to draw samples from the t distribution with 30 degrees of freedom, and do so by transforming z draws only. In other words, for that homework problem, you are only allowed to draw samples from the normal distribution, the standard normal distribution, so not the chi-squares. However, we have talked about how we can get chi-square with 1 degrees of freedom from samples of z's. Well, how do you get from chi-square 1 degrees of freedom to chi-square of new degrees of freedom? We will talk about that in the next subsection, which involves the convolution or the sums of random variables. Another notable relationship is the one between uniform random variables, pairs of uniform random variables, and pairs of independent z distributed or normal 0, 1 distributed random variables. So suppose that y1 and y2 both follow the uniform distribution between 0 and 1. Then, if we apply what is known as the Box-Moeller transformation, where we set z1 to be equal to the square root of -2 natural log of y1 times the cosine of 2 pi times y2, and we set z2 equal to the square root of -2 times the natural log of y2 times cosine of 2 pi y1, then we can show that z1 and z2 are independently distributed and both of them have the standard normal distribution. So we're not going to talk about any of these proofs here. You probably have seen some of them in the 410 class. For the rest of them, I think a more advanced math stats class like 510 will prove them. For example, I think for the Box-Muller transformation, it's a very famous homework problem from the Casella and Berger math stats book.